Okay, so I'm going to walk through just kind of a concept map of chapter 7, and we'll see if we need to dive into any additional details. And chapter 7 and 8 are just going to kind of flow together, honestly, too. It'll just like keep building. It's just like spread out over 2 chapters. And the point of this one is going to be all about bonding. And we've spent some time already on ionic bonding. Can't even spell it. And that we can predict ionic compounds they'll form from 2 different elements. And we can like take an ionic compound and say, oh, the charge on the metal is this, and the charge on the non-metal or polyatomic ion is that. And so like those are important skills. This chapter will go in a little bit more depth and start talking about lattice energies, which helps explain a bit of like why some ionic compounds dissolve in water and some don't. And we'll talk about that more also when we just think about enthalpy of dissolution in Chem 162. But it's really starting to come back to like based on the charge and the size of the atoms, like how close the charges are to each other, and their magnitude, like is it a +5 or a +1? And like attracted to a -1 or a -5 charge, will have different forces of attraction between it. And that's really just coming all from Coulomb's law, which is the larger the charge, and if they're opposite, the stronger the attraction, and the shorter the distance between those charges, the stronger the attraction. And so all of that's just out of Coulomb's law, which I feel like I just say Coulomb's law like is the reason for everything that we're doing in this chemistry class, but it's probably true. So that's one piece of this, and it's kind of the smaller component. I think the more important part of this chapter, what we'll build into chapter 8 with, is covalent bonding. And there's kind of like there's 2 ways to think about what is a covalent bond. Like overall, this is sharing of electrons between 2 atoms. And so what that really means is that an electron on one atom is attracted to its nucleus, but it's also attracted to the nucleus of another atom. And so we're still looking at Coulomb's law, right? It's still opposites being attracted. It's just in this case, it's like a negative charge being attracted to 2 positive charges on 2 different atoms. And that creates our covalent bond. So that's like what it is, but like kind of defining when is something covalent versus ionic. The short answer is, so like to this question of when, is typically when it's 2 nonmetals or more, 2 or more nonmetals that are forming a compound. And I love that answer because like metalloids will also form covalent bonds with nonmetals. Also, we have examples of metals and nonmetals forming a bond that is more like a covalent bond than an ionic bond. And iron and sulfur is one example of that your body like takes advantage of with some of the enzymes that you have inside of you. So the short answer isn't great, but it's a nice, like, I'm staring at a compound, is it covalent or ionic? Like, this is a good place to start. The longer answer has to do with electronegativity difference, which we abbreviate delta En. And so if this is going to be less than 1.9 and greater than or equal to 0.5, and that's just the difference between the electronegativities of 2 atoms that are participating in a type of bond. Sorry, not 0.5, let's go 0. Let's just say less than 1.9. Then we have a covalent bond. Electronegativity is kind of like electron affinity in a way. There's a lot of different measurements for the electronegativity of any element, but like it kind of depends on the environment that it's in. And so like if you search up an electronegativity table like that's like going to just share the assigned electronegativity for different elements, like I can come up with like 4 different ones that have slightly different values for different elements. And so it's not like this thing you can kind of calculate from first principles. It's instead something we measure, and everyone has kind of a different method. So there's a few different things reported. But it's really kind of telling us how tightly electrons are held in the atom, or how much they're attracted to that nucleus. And it's really those valence electrons. Valence electrons. But I recommend like just kind of keeping a chart handy. The overall trend for this is that electronegativity increases up the periodic table and up to the upper right-hand corner. So like fluorine has the highest or largest. It's equal to 4.0. So it's like on a 4.0 scale. Okay, so that's what a covalent bond is. So within that, then we can kind of, I guess, okay, so before we get into like characterizing this and like trying to decide how atoms are arranged, another piece of covalent bonding is we can review the different strengths of it. And this is going to be captured by the bond enthalpies, which should hopefully be familiar from chapter 5. And it's really like how much energy, in terms of like being able to transfer heat, is stored in a chemical bond. And so this is kind of thinking through the lattice energies and like how that tells us about different strengths of ionic bonds. The bond enthalpies will talk about the different strengths of covalent bonds. Right. So that's all important, but I think the real piece of this is like trying to represent covalent molecules. And this is really a complicated question at the end of the day. And hopefully after studying like the electronic structure of the atom, like the level of complicated of like what is an electron doing is like hopefully still fresh. And so like take all those problems when we were talking about where's the electron in the atom, and now we're like, well, now the electron is kind of spread out over these 2 atoms, and it's like it just compounds the problem. So while we can like solve and actually have like, or we can get a lot of information about like 1 electron and just imagining it in a box, it's really hard to get information about more complicated systems. We do a lot of approximations. We have to like crunch a lot of numbers using supercomputers. Fun stuff, right? Computational chemistry. And so we actually have lots of different ways of like essentially a lot of rule sets that allow us to make predictions and approximate. That makes things a lot easier for us to kind of represent and to be able to work and predict and manipulate molecules. And so we have a few different theories that we're going to use to kind of like build a picture of what covalent bonding looks like and what covalent molecules look like. So the simplest is Lewis dot theory or Lewis theory. And then we build up to Vesper theory. And then we're going to explain this with valence bond theory. Oh no. And finally, molecular orbital theory. Which is like my personal favorite. So these 2, we're going to do these in chapter 8. And Lewis theory and Vesper theory we'll focus on in chapter 7. So Lewis theory is going to give us Lewis dot structures, which will be like in 2 dimensions. And Vesper theory will give us a picture that is in 3 dimensions. Which will be really important actually later. When we start talking about intermolecular forces, because having an idea of the molecule in 3 dimensions will allow us to predict polarity, which we'll use to understand intermolecular forces in Chem 162. So we'll use that a lot. All right. So I'm going to dive into Lewis theory and then Vesper theory. I'm going to take a quick pause and see if there are any questions. Okay, let's start with Lewis theory. So this is really a bookkeeping method. Like I'm going to keep track of some electrons, kind of like electron configurations, right? Like clearly chemists like tracking where electrons are, even though we have no idea where they are. So like this is going to be a pattern that we can use, or an algorithm that we can use to make predictions about what something might look like. And so it's a good rule set to learn. And we can use it as basically a shortcut to thinking about what something's polarity would be and use Vesper theory with it. So the idea that this hinges on is the Lewis dot symbol. This is going to focus on just the valence electrons. So like carbon has 4 valence electrons. So its Lewis dot symbol looks like this. So you think about a box and you put your chemical element symbol in it. And then each box can hold space for 2 electrons, or each side of the box essentially. And so you can have up to 8 valence electrons, right? Except for hydrogen and helium. And so you can place the valence electrons. People usually go clockwise. And you're going to place 1 on each side before pairing. So for carbon, carbon has 4 valence electrons. So it's got 1, 2, 3, 4. And that's how we get this valence, Lewis dot symbol right here. If instead I had like oxygen, which has 6 valence electrons, then I would write that oxygen symbol O. I'd start at the top and I'd work around at 1, 2, 3, 4. Now I start pairing 5, 6. And so these kind of pairs right here that are paired up like this, these will typically become lone pairs in our Lewis structures. And the unpaired ones right here, these are typically the ones that will form bonds. Again, this is a bookkeeping method. This isn't actually what happens. And like, this isn't actually how electrons are arranged in an atom at all. And so, like, we're not going to do stuff that's like based in reality. In that sense, we're just doing something that predicts things well. So from these like electron dot symbols, we can then build Lewis structures. So these Lewis dot symbols are going to lead to Lewis structures. When building a Lewis structure, your goal is to have an idea of how the atoms are arranged and how they're bonded to one another. Oh my, sorry, I apparently switched page. So you're going to try to match up these electrons together, or sorry, match up these atoms and arrange them. So we're going to arrange atoms into structures that represent the chemical. You're going to do it so they share electrons. So each element has 8 electrons, either in lone pairs or in bonds. The exception, of course, is helium and hydrogen and like boron. There's not a lot, sorry. There's like a couple ways people teach this. The way the book does it, the way the homework does it, the way most videos out there do it, I don't like. It doesn't really work for my brain. A lot of them say to just start with something in the middle, arrange the atoms, and then put all the electrons in on top of it. And I notice students create some really bizarre structures that then you do the double check of formal charges, and you then have to start all over. And there's a few rules, like start with the least electronegative in the middle, that are helpful, but it really relies on a lot of chemical intuition. And if you're starting with no chemical intuition at all, that feels very challenging, especially like the blank page sort of thing. So I've got a system for this that I like to use that doesn't rely on chemical intuition at all, and is kind of like a rule set that you can follow even when you like have no idea what to do. So I'm going to give the short version of that, and then with an example, and then I'll pause. Okay, so let's say I'm going to build a Lewis structure for, like, let's just do carbon dioxide as my example. My steps that I'm going to follow here are predict the number of bonds for each element. I'm going to start with the element that needs the most bonds in the center. And then I'm going to add atoms around that that need less bonds. I'm going to add bonds that need, or elements sorry. I'm going to add elements that need only one bond to meet that octet rule last. And before that, I'm going to figure out if I need any multiple bonds. So predicting the number of bonds for each element. So carbon has 4 valence electrons. So if it's going to reach an octet of 8, and it has 4 electrons, it needs 4 other electrons that are shared with it, right? And so that's going to be the number of bonds that it tends to form. Not always. Sometimes, like, there's a negative charge, and so things are different. Or sometimes it does something weird, kind of like ozone, right? But this, like, gets us through a lot of structures this way. Oxygen has 6 valence electrons, so for it to reach an octet, it's going to need 2 bonds. So carbon has the most, so I start with carbon. I'll put it in the middle, and I'll draw the Lewis symbol for it. And one of my big strategies here that's a little bit silly is I essentially play connect the dots with the Lewis symbols. And my goal is to connect all the unpaired electrons. So I'll put in oxygen next. And I'll just, like, put it here, and you can put it wherever, right? And I'm going to again put its Lewis dot symbol here. And so when I say connect the Lewis dots, what I mean is I'm going to match up 2 unpaired electrons. Oops. And that's going to create a bond. So now I have one single bond if those 2 electrons are shared with one another. All right, and I'm going to put in my other oxygen. I'll put it down here just for fun. All right, and I match these up, right? Okay, so then if I look at this, I still have 4 unpaired electrons. And I have no more atoms that I can use to form bonds, right? And so I need everything to have an octet, and so like this won't happen right now. So with these 4 unpaired electrons, I always take the number of unpaired that remain and divide by 2, and that's going to equal the number of bonds I still need to form, or the number of multiple bonds. So I need 4 divided by 2. I need 2 more multiple bonds. So I'm going to use some double bonds. Another way of thinking about it is like I'm again connecting the dots. Like I can connect the dots between these 2 unpaired electrons, between the carbon and oxygen, and this oxygen and carbon here. And so I'm going to rewrite this. And I'll have oxygen double bonded to carbon, double bonded to oxygen. Note a few things here. One, if I have 2 electrons that are in a lone pair, I leave them alone. And I'm also representing 2 electrons as a single line. Okay, so Lewis structures, that might have been a little simple. I'll try to speed up here. So then the next thing is formal charge, right? So I double check in a couple of ways. One, I make sure each element has, or each atom has a octet of electrons or duet. And then I can also, check the formal charges. And formal charges are going to be equal to the number of valence electrons minus the number of non-bonding electrons minus the number of bonds to that atom. So, for example, this oxygen right here has a formal charge equal to 6 minus the 4 electrons in the lone pairs minus the 2 bonds of 0. And I'm trying to minimize formal charge. I can also look at the oxygen and say, okay, it has 4 electrons in lone pairs, and it has 2 bonds, each with 2 electrons. So it has a total of 8 electrons around the oxygen. So it's following the octet rule too. And so that's kind of my double checks for these. And that is Lewis dot structures kind of in a nutshell. Sometimes you'll have things called resonance structures. Actually, wait, before that, sometimes you'll have polyatomic ions. If you have a polyatomic ion, you get to add or subtract any electron you want. So for example, if you had OH minus, when you're building this, you get to add 1 electron anywhere you want in the structure because it has a -1 charge. If you had something like SO4 -2, then you would have 2 electrons that you could add because you have that -2 charge. And then resonance structures are kind of like a hybridization. Because Lewis structures are just like an estimate, right? Like it's a bookkeeping method. It doesn't always match what we see in reality in terms of like the bond lengths. So like a double bond will be shorter than a single bond. And so for something like, so like if you have like alternating single or double bonds, then you could have a resonance structure by rearranging those. So in these ones, it looks like structurally the same. So everything, all atoms are attached in the same way. So all atoms have the same arrangement. But the electrons are arranged differently. So like in something like benzene. Of course, I choose one that takes too long to draw. I can draw a resonance structure. I use a double arrow where I essentially take each of these double bonds and single bonds and swap them. And it'll look the same, but it's like if I labeled each of these carbon atoms, it would be a different arrangement of like which ones were single bonded or double bonded. And then I see that's what we would call a resonance structure. And like together, the hybrid structure, sorry, I'm going fast, it's kind of the average of the two. And so it would look something like you would just have like double bonds all the way around, like. And like each of these bonds is really 1.5, which would be the average of our two resonance structures. And so this helps us make better predictions about like how the molecule actually behaves and looks. So with this as the base, then the chapter is also going to go into exceptions to the octet rule. And we've already kind of mentioned like hydrogen and helium follow a duet rule. So they will only want to have 2 electrons around them. Boron is going to only want 6 electrons. It's weird, it's a metalloid. And then everything in the 3rd row and below will be able to expand its octet. Which means it can have greater than 8 electrons around it. And what it's doing is populating and using the d orbitals, the empty d orbitals, to expand that octet and have more electrons. So like the classic example of sulfate, right? Is that this sulfur right here actually has 1, 2, 3, 4, 5, 6 bonds around it, and each one has 2 electrons. So it really has 12 electrons around it instead of 8. All right, that's my summary of Lewis theory. I'm going to take a quick pause and see if there's any questions. All right, now we're going to talk about Vesper theory, which again is just trying to look at this in 3 dimensions. And so we are going to use our Lewis structures. So that's our starting point. And then we're going to evaluate each central atom. Sorry. And so these are going to be anything that is bonded to 2 or more things. And what we're going to find is like, how are things going to arrange themselves in space? So how do atoms and lone pairs arrange themselves in space? And we're going to give those arrangements names, and those will be molecular geometry names. And we can report bond angles. And so kind of the key idea for like this question of how do they arrange themselves in space is that anything that it has electrons will repel each other. So the electrons are going to repel each other. So that means that lone pairs and bonded atoms are going to try to get as far apart from one another as they can. So like for carbon dioxide, right? This carbon right here is our central atom. Those oxygens aren't bonded to anything else. It has 2 atoms bonded to it and no lone pairs. So the furthest 2 things can get from one another is 180 degrees. So this is going to have a bond angle of 180 degrees. And we're going to call this shape linear. I recommend taking a look at the chart of all the different geometries. There's just going to it's good to just have one handy that you'll review. And so you'll just need to review the geometry names. And these will all be decided based on the number of bonded atoms and the number of lone pairs. And there's a bunch of them. There's a bunch. And we'll go all the way through basically octahedral. So I would like you to know linear all the way through octahedral. And we'll use some of those weirder shapes that are kind of like octahedral in 163 a lot when we talk about transition metal complexes. And it'll be really fun. Yeah, and so that's VSEPR theory. And it takes a little bit of practice in getting used to the names because they're weird. They're like trigonal planar and trigonal pyramidal, and the names are going to be based on the atoms that are bonded, but the arrangement is based on all of these electrons. So these will determine the arrangement in space. But we're going to name the geometry just on the bonded atoms. And here's the trick. You're going to get a geometry name for each central atom. You're only going to have a geometry or a shape name for the whole molecule if it's an extremely simple molecule with only one central atom. Most molecules are not that simple. And so you'll have geometry names for each of those central atoms. And the overall geometry is just like a blob in space that's changing constantly. And so we don't name the entire molecule's shape, just at those central points. And the reason we do this then is to think through polarity. And so once we have a 3D shape for something, so once we have our 3D shape and we can draw it, so once we have our 3D shape, you should draw it with wedges and dashes, sorry. So we can represent something in space. So let's say we have a carbon and it's bonded to a hydrogen and a hydrogen. So if you had 4 things around a central atom, they would all be 109 degrees apart. And so we use these wedges and dashes to have kind of a shorthand for drawing in 3 dimensions because most of us are terrible artists. And so solid wedge is coming out of the board or the paper, and a dashed one is going back into the paper. And so once we have this shape, then we can identify any polar bonds. And then we can decide by kind of doing a average of vector if the molecule is polar. And we're going to come back to that electronegativity difference that we talked about that made something a covalent versus an ionic bond. Anything that is a 0.0 to 0.49 difference in electronegativity is going to be what we just call nonpolar or covalent. And anything that's 0.5 to 1.9 difference in electronegativity will be polar covalent. And so that electronegativity difference is just going to be equal to the electronegativity of one atom minus the electronegativity of another atom. We usually look at the absolute value, and these have to be bonded together. And so we identify these polar bonds. So I'll put up that carbon dioxide again. Okay, so here's carbon dioxide. We can represent it a couple different ways. So my oxygen electronegativity difference between my carbon and oxygen bond is equal to 3.5 minus 2.5. So it equals to 1.0. So therefore it is a polar bond. And so I can either represent that with an arrow going along the bond like this, or I can represent it with a little delta minus and delta plus along the bond. And so what this delta minus delta plus means right here, delta plus is a partial positive charge, and delta minus is a partial negative charge. So you can use either one with me. Some people, like instructors, have a preference. I really don't care. And then to determine the overall polarity, so this has two polar bonds. I'm going to see if my two dipole moments actually cancel out. And in this case, they do. I essentially take the sum of the vector math here, and they would cancel out. They're going to be pulling in exactly opposite directions. So this is a nonpolar molecule that has two polar bonds. And then this will later on dictate if it dissolves in fat or water. And in this case, if it's nonpolar, it will dissolve in a fat. And so that's why we use polarity. All right, and I'm going to pause there.